Okay, let's unpack this. We're doing a deep dive today into, well, a language that feels almost ancient in tech terms, right?
Uh-huh.
But it's still absolutely critical. I mean, fundamentally part of how everything works. C,
That's the one.
the language that built Unix, the core of Linux, and it's
Yeah.
just quietly running so many systems we use every single day, things you don't even think about.
Exactly.
So how does something from the 70s stay so vital, so essential here in 2025?
It's a fascinating story, really. C has this kind of enduring power because of the balance it struck right from the start.
What kind of balance?
Well, it's this unique mix of efficiency, getting close to the metal portability, and crucially, that low-level control it gives
It's
programmers.
real power.
Immense power, yeah.
Yeah.
But, with just enough structure on top to make building big, complex things actually possible, though definitely challenging.
And that story, that power, that tricky balance, that's what we're digging into today. We got a whole stack of sources here, articles, papers, notes, giving us the full picture of C's journey.
Right.
So we're going to use these to guide our deep dive. We'll look at where C came from, its ancestors like BCPL and B. We'll break down why it was designed the way it was.
The core principles.
Exactly. Then the nuts and bolts, syntax, data types, control flow, and of course the big one, manual memory management.
Ah, yes. The power and the peril.
Definitely. The risks, the responsibilities involved there. We'll also look at its standard library, the tools it gives you, and just how many modern applications still rely on C. It's quite surprising.
It really is. And we'll compare it a bit to the languages it influenced, naturally.
Yeah. And finally, we'll touch on, how you might learn C today and why its future, particularly in certain fields, looks surprisingly solid.
Exactly. Think of this as getting to grips with the bedrock. So much modern computing is built right on top of C.
Okay.
We'll explore its elegance, which can be kind of hidden sometimes, the sheer power of getting close to the hardware. But also, importantly, we need to face those sharp edges. That responsibility it puts right on the programmer.
Okay, let's do it. Get ready to explore the foundations. Let's dive in.
All right.
So, to really understand C, we have to go back. Way back. It didn't just appear out of nowhere, right? The sources trace its lineage. BCPL. What's the story there?
Well, it's interesting how it all stems from practical needs. BCPL, Basic Combined Programming Language, came first, mid-60s, from Martin Richards.
Okay.
It was designed for writing compilers, system software, untyped language. Then Ken Thompson at Bell Labs built on that to create B around 1970.
B for Bell Labs
Or maybe. But B was specifically for writing utilities for the very early Unix system they were building. First on a PDP-7, then later, critically, for the PDP-11.
Okay, so B was the first language used for Unix tools, essentially.
Pretty much, yeah. It was a systems language for its time, but it had problems, especially on the PDP-11.
What kind of problems?
Well, the sources point out B was interpreted, so it was relatively slow. But the bigger issue on the PDP-11 was memory access.
How?
The PDP-11 could address individual bytes in memory byte addressability. B, however, mostly worked with machine words. This made handling characters, single bytes, really inefficient. They needed something faster and something that could work directly with bytes.
Got it. And that's where Dennis Ritchie comes in, the name everyone knows.
Exactly. Ritchie, also at Bell Labs, started work around 1971 specifically to improve B. His goal was a compiled language, more efficient, and crucially, adding data types, especially character types, to really leverage the PDP-11's architecture and fix B's byte handling issues.
So this early version was called NB New B.
Yeah, sometimes called NewB or NB initially. He was basically fixing B for the hardware and for Unix's needs.
It sounds very practical, very problem-driven.
Absolutely, and that's key to C's origin. It wasn't an academic exercise. It grew organically to solve immediate problems faced by the Unix team. Ken Thompson started using NB right away for parts of the Unix kernel.
Oh, wow. So the user was right there giving feedback.
Instant feedback loop. Thompson's needs directly shaped Ritchie's ongoing work. It was this rapid, iterative development driven purely by the practical demands of building Unix.
That makes sense. So Ritchie kept adding things.
Through 1972, yes. He added more sophisticated data types, not just char, but integer arrays, floating point numbers, structures for grouping data, and critically, pointers.
Ah, pointers. We'll get back to those.
Oh, yes. Pointers allowed direct manipulation of memory addresses, and he improved how functions could return different data types, not just integers. With a new compiler for all this, the name changed. It became C.
1972, the birth of C.
His goal
An efficient, practical systems language for Unix.
Precisely. And the moment that cemented C's importance came really quickly, in 1973.
What happened then?
The sources really emphasize this. They rewrote almost the entire Unix kernel in C.
The kernel, in a high-level language.
Yeah.
That must have been radical.
It was revolutionary. Kernels back then were almost exclusively assembly language. Maximum performance, direct hardware control, that was the thinking.
So rewriting Unix in C proved something important.
It proved that a higher-level language could be efficient enough for the absolute core of an operating system. It was a massive paradigm shift.
That really speaks to C's design, doesn't it?
It does. C wasn't cooked up in isolation. It was made by programmers for programmers working on a real complex project. It had to be practical, multi-purpose, and solve the actual problems they were facing. It's often called a practitioner's language for that reason.
Okay, let's dig into those core design principles that came out of this practical approach. The sources mention 3 pillars.
Yeah, they're fundamental. Pillar 1, efficiency. The absolute main goal was generating machine code that was fast and small, very close to what you could get with hand-tuned assembly. Critical for systems work.
Speed and size. Got it.
Pillar 2, portability. This was a big deal compared to assembly. C was designed so you could compile and run the same code on different machines, different operating systems with minimal changes.
That's huge. That allowed Unix and C programs to spread, right?
Exactly. And pillar 3, power and flexibility. This is where C gets really interesting. It gives you low-level access. You can twiddle bits, access memory addresses directly, almost like assembly.
But with more structure.
Yes, but within the structure of a higher-level language, you have loops, functions, data structures.
Yeah.
This mix is why people call C a middle-level language.
Middle level.
Okay.
Not as abstract as Python, say, but way above assembly.
Precisely. It doesn't hide the machine from you. You still see hardware details, like how integer sizes might vary. But this transparency gives you immense control, essential for OS kernels, drivers, embedded stuff. It gives you structure that assembly lacks, but crucially, it doesn't shield you from making mistakes the way many higher-level languages try to.
That middle ground.
Yeah.
Still relevant today for certain tasks.
Absolutely.
Now, as C took off with Unix, different people started writing compilers for different machines. Wasn't there danger of the language splintering? Different dialects emerging?
Yes, that was a real risk. As C spread beyond Bell Labs, vendors implemented it on various platforms, and small differences crept in. Code that worked perfectly on one system might break or just behave slightly differently on another.
Undermining that portability goal.
Exactly. So formal standardization became essential to keep C consistent and truly portable.
But before the official ANSISO standards, there was the book, right? K&R?
Ah, yes. The legendary The C Programming Language by Brian Kernighan and Dennis Ritchie, first edition in 1978. For years, that book was the standard, the de facto definition of C.
So concise, so influential.
Incredibly. When people refer to KNRC, they mean the language described in that first edition. It really set the stage for the formal process.
Okay, so K&R was the unofficial standard, then came the official committees.
Right. ANSI, the American National Standards Institute, stepped in. They published their standard in 1989. That's ANSIC, or C89. Then ISO, the International Organization for Standardization, adopted the ANSI standard pretty much wholesale in 1990. That became ISO C, or C90.
C89 and C90 are essentially the same thing now.
Basically, yeah. Minor differences, mostly in formatting. This formal standard was crucial. It gave everyone a single, agreed-upon definition, making source code portability a reality across the exploding variety of computers and compilers.
And C didn't stop evolving there, did it? There were later standards.
No, it kept evolving, though maybe more slowly than some other languages. The standards process incorporated new features based on how people were actually using C and what new hardware could do. C99 came along in 1999.
What did C99 add?
Some significant things. Inline functions, as hints to the compiler for optimization. Variable length arrays, VLAs, letting you declare arrays whose size isn't known until runtime. A bigger integer type, long int. And maybe most visibly, the single-line comment style, borrowed from C++ pair.
Finally. Comments, so useful.
Definitely. C99 also added better support for Unicode characters and improved math functions.
Okay, then C11.
C11 arrived in 2011. Key additions there included built-in support for multi-threading via threads.h. It's fairly basic, low-level threading, mind you. More Unicode improvements, things like nor_turn to tell the compiler a function never returns, helping optimization, and finer control over memory alignment with alignus and alignoff.
Alignment control. Sounds very low level, very hardware focused again.
It is, yes, very C. Then C17 in 2018 was much more minor, mostly clarifications and bug fixes for C11. No big new features.
And now we're looking at C23.
Yes, C23 is the next revision, expected around now 2024, maybe early 2025. The sources suggest features aimed at modernizing things a bit more, while keeping the core C spirit. Things like a native bool type, moving beyond C99's bool, pointer improvements, maybe making them a bit safer or clearer, and standard attributes, a structured way to give metadata to the compiler about code.
So C keeps moving forward, incrementally adapting.
Exactly, staying true to its roots but incorporating necessary updates.
Great overview of the history and evolution. Let's shift gears now to the code itself. If I look at a typical C program, what's the structure? What are the basic syntax rules?
Okay, yeah, the structure is usually pretty logical. The sources lay it out well. You often start with a documentation section comments explaining the program for single lines. For multi-line blocks, good comments are vital.
Absolutely.
What comes next? The link or preprocessor section. This is where you use #include to bring in header files, like #include stadio.h for input-output. The preprocessor handles these before compilation. You also see #define here, creating symbolic constants or macros.
Like #define PI 3.14159.
Exactly. Sometimes these #defines get their own definition section. Then comes the global declaration section. This is for variables accessible everywhere, global variables, and also for function prototype.
Prototypes, what are those?
A prototype tells the compiler a function signature, its name, return type, parameter types, before the compiler sees the function's actual code. It's crucial so the compiler knows how to handle a call to that function correctly, even if the definition is later in the file or in another file entirely.
Got it. And the heart of the program.
That's the main function. Every C program you can run needs one. Execution always starts in main. The standard way and the modern way is int main. It returns an integer exit code to the OS0, usually means success.
I've seen void main sometimes.
You might see it in older code or some specific embedded context, but int main is the portable standard you should use.
And other pieces of code, the reusable blocks.
Those are your user-defined functions. You write these to perform specific tasks, breaking your program into smaller, manageable chunks. Main calls these functions, and they can call each other.
Okay. Basic syntax rules.
Key ones. Every statement ends with a semicolon. And code blocks, like the body of a function or the code inside an if or while, are enclosed in curly braces.
Semicolons and curly braces. So familiar from other languages.
Totally. C's influence is huge there. Now let's talk about the basic ingredients C works with, the data types.
Right, the fundamental types of information.
C gives you the basics. Char for single characters, which are really small integers, various integer types, int, short int, and long int for whole numbers of different sizes, and floating point types. Float, double, long double for numbers with decimal points.
And the sizes of these, like how many bytes an n takes up, can vary.
Yes, that's a key C characteristic. The standard guarantees minimum ranges, but the exact size of an int or long can depend on the machine architecture and compiler. An int might be 16 bits on one system, 32 or 64 on another.
Why is that?
It allows the compiler to choose the most efficient natural size for the underlying hardware, contributing to C's performance. The sources usually show typical sizes and ranges, and the format specifiers like % for int, % for float, % for char, used in functions like print.
Okay, and you can modify these. Signed, unsigned.
Yep. Integer types are signed by default, can hold positive and negative values. You can specify unsigned if you only need non-negative values, which doubles the maximum positive value they can hold. Void is special. It means no type, used for functions that don't return a value or for generic pointers.
What about true-false? Boolean.
Good question. Originally, C had no dedicated Boolean type. Programmers use integers. 0 for false, anything non-zero for true. C99 introduced bool, which holds 0 or 1. You usually include stdbool.h, which defines bool as a macro for bool and gives you true and false constants. C23 is making bool a proper keyword.
Okay, those are the building blocks. How do you create more complex data structures?
C lets you build them up. You have derived types like arrays, sequences of the same type, and pointers, which we'll get to. And user-defined types like struct, which lets you group different data items together under one name, like a record. Union lets different types share the same memory space. And enum creates named integer constants. These are your tools for organizing related data.
So how do we actually store and use data values during the program? Variables and constants.
Right. Variables are named memory locations where you store data that can change. You must declare a variable before using it, telling the compiler its type and name. like int counter. You can also initialize it with a starting value at declaration. Int score equals 0.
And constants are values that don't change.
Exactly. Fixed values. Two main ways to define them. Using the preprocessor. Hashtag define maxitems 100. The preprocessor literally replaces maxitems with 100 everywhere in the code before compilation.
Like a simple text replacement.
Pretty much. The other way is the const keyword. Const float gravity equals 9.81. This tells the compiler that the variable gravity cannot be changed after initialization. The compiler enforces this. Const is generally preferred over hashtag define for constants nowadays as it's type aware.
Okay, where you declare a variable matters too, right?
It's scope. Absolutely. Scope defines where a variable is accessible and how long it exists. Variables declared inside a function or a block are local variables. They only exist and are accessible within that function or block. Their memory is usually on the stack and vanishes when the function block exits.
So they're temporary.
Right. C89 required you to declare all local variables at the very beginning of a block, but newer standards, C99 onwards, let you declare them closer to where you first used them, which is generally clearer.
And global variables.
Global variables are declared outside any function. They exist for the entire lifetime of the program and can be accessed and modified by any function after their declaration point.
But the sources advise against using too many globals.
Strongly advise, yes. It's a general good practice. Too many globals make it hard to track who changes what, leading to bugs that are difficult to find. It makes code less modular and harder to reason about. Passing data via function parameters is usually much cleaner.
Okay, so we have data types, variables, constants, scope. How do we actually do things with the data? Operators.
Yep. Operators are the symbol C uses for operations. You've got the basics. Arithmetic operators like plus air, ampersand, modulus for remainder. Relational operators for comparison, not equal to air. These return true, non-zero, or false zero.
Like checking if count 10.
Exactly. Then logical operators, and logical AND, logical OR,
Right.
logical not T, for combining or inverting true-false conditions.
And bit level stuff.
Yes, C has bitwise operators, and bitwise AND, bitwise OR, bitwise XOA, bitwise N not T, left shift, right shift. Very powerful for low-level manipulation, working directly with the binary representation of data.
Okay, what else?
Assignment operators. For simple assignment plus compound assignments like plus O's as shorthand, or e.g. x plus 5 is x plus 5. Increment decrement operators, plus, add 1 and subtract 1, often used in loops. The conditional or ternary operator is a compact way to write an if-else expression. Result, score 60.
PF.
Haha, the ternary operator. Concise, but can get hard to read if overused. True. And finally, the size of operator, which tells you the size, in bytes, of a variable or a data type at compile time, like size of int. Very useful for memory allocation and portability.
And the order of operations matters, like in math.
Yes, C has strict rules for operator precedence, which operators are evaluated first, e.g. before plus, and associativity, how operators of the same precedence are grouped, e.g. left to right for Planck. You can always use parentheses to force a specific order.
Got it. So we have data, operators.
Yeah.
How does the program make decisions or repeat things? Control flow.
Right. This is how you make programs do more than just execute instructions sequentially. For conditionals making decisions, you have if. Execute code only if a condition is true.
If. This is your do something.
Exactly. Then if else. Do one thing if true, another if false, and the if-else if ladder for checking multiple conditions in sequence.
Red switch.
Switch is good when you have multiple choices based on the value of a single integer expression. You have different case labels for specific values and an optional default case if none match.
But switch has that famous trap, doesn't it? The fall through.
Ah, yes. The infamous fall through. Once a case matches, execution starts there and continues into the next case's code block unless you explicitly put a break statement at the end of the case.
So if you forget break, you can accidentally execute code from multiple cases.
Exactly. Sometimes that's intentional, but usually it's a bug. You have to remember those break statements.
Okay, noted. What about repeating actions? Loops.
C gives you 3 main loops. The for loop is great when you know roughly how many times you want to iterate, or you have clear initialization, condition, and update steps. The example for int I equals 0, I10, I++ is classic. Initialize I to 0, loop as long as I is less than 10, increment I after each loop.
Very common structure.
Yep. Then the while loop. It checks the condition before each iteration. The loop body only runs if the condition is true. If it's false initially, the loop never runs.
Check, then run.
Right. And the do while loop checks the condition after the loop body runs. This means the body is guaranteed to execute at least once, even if the condition is false initially.
Run, then check. Okay. What if you need to jump out of a loop early or skip an iteration?
You use jump statements, dot break, which we saw in switch, also works in loops for while do while. It immediately exits the innermost loop you're in.
Jumps right out.
Yep. Continue is used only inside loops. It skips the rest of the current iteration and jumps straight to the next iteration's condition check, or the update step in a for loop.
Skips ahead within the loop.
Exactly. And then there's goto.
Uh-oh. The one programmers are told to avoid like the plague.
Pretty much. Goto lets you jump unconditionally to a specific labeled point, label, within the same function. While it's part of the C standard, its use is heavily discouraged because it makes code incredibly hard to follow and debug. It creates spaghetti code.
Jumps all over the place.
Right. There are very rare specific edge cases, like breaking out of deeply nested loops, where some might argue for it, but honestly, there's almost always a better, clearer way using structured control flow. Just avoid goto.
Sound advice. So these control flow tools let programs make decisions and repeat actions in a structured way.
Exactly. Building blocks for program logic. Again, you see these structures echoed in so many other languages.
Okay, moving up a level. We need to organize code into reusable chunks, right? Functions.
Absolutely. Functions are the core way to structure C code. You break your program down into functions, each performing a specific, well-defined task. This makes code modular, easier to understand, easier to test, easier to reuse, easier to maintain. Essential for anything non-trivial.
You mentioned prototypes earlier. Is that related to declaration versus definition?
Yes, exactly. A function declaration, the prototype, just tells the compiler the function's interface, its name, what type of value it returns, its return type, and the types of data it expects as input, its parameters, like in add, in x, in y.
Just the what, not the how.
Right. Prototypes usually go at the top of the file or in header files. The function definition is where you provide the actual code, the implementation, the how. It includes the function header, which looks like the prototype, followed by the code block containing the function's logic.
So the compiler sees the prototype first, knows how to call it, and links it to the definition later.
Correct. Now, getting data into a function. Parameters are the variables listed in the function's header in the declaration and definition. Arguments are the actual values you pass to the function when you call it.
Like result,
Yeah.
add 5, 3.
Yeah.
5 and 3 are the arguments.
Yes. And C, by default, uses call by value. This is really important. When you pass an argument, C makes a copy of that argument's value and gives the copy to the function's parameter.
A copy. So if the function changes the parameter's value.
It only changes the local copy. The original variable back in the calling code is completely unaffected.
Okay, so if I pass my var to func, and inside func I do p equal 100, my original myvar doesn't change.
Exactly. P gets a copy of myvar's value, and only that copy is changed. This prevents functions from having unexpected side effects on the caller's data.
Yeah.
But this leads us neatly towards pointers.
Because pointers let you get around this.
They provide a way to simulate what's called call by reference, where the function can modify the original variable. We'll see how. But first, how does a function send data back?
Return values.
Right. A function can return a single value using the return statement. The type of value it can return is specified by the return type in its declaration. If a function doesn't need to return anything, its return type is void, and you might use return without a value, or just let execution fall off the end.
One value back. Okay. What about recursion?
Recursion is when a function calls itself. It's a powerful technique for solving problems that can be broken down into smaller, self-similar subproblems. Think calculating factorials or traversing tree structures.
Needs a way to stop, though, right?
Absolutely critical. A recursive function must have a base case, a condition under which it stops calling itself and just returns a value directly. Otherwise, you get infinite recursion and crash with the stack overflow.
The source had a simple multiply function example. How does that fit in?
Yeah, it shows the basics nicely. You see the prototype, int multiply, int a, int b, tells the compiler the function signature, then the definition, int multiply, int e, int b, return a b, the actual code, and finally the call in main, int result multiply, num1, num2, passing arguments num1, num2, and storing the return product and result. Simple illustration of declare, define, call.
Okay. Functions bring structure. Now, the topic everyone finds either fascinating or terrifying.
Pointers. Pointers, yes.
Yeah.
This is where C really shows its low-level nature and where a lot of the complexity and potential for bugs lies. Fundamentally, a pointer is a variable that holds a memory address.
Not the data itself, but where the data lives.
Exactly. Think of memory as numbered boxes. A normal variable int x equals 10 puts 10 in the box.
Right.
A pointer variable int p is designed to hold the number address of a box that contains an integer.
How do you declare one? That asterisk.
Yep. Data type pointer name. So int ptr declares ptr as a variable that can hold the address of an int. Float fptr holds the address of a float, and so on. The indicates it's a pointer.
Okay, so PTR is ready to hold an address. How do you get an address into it?
You use the address of operator, the ampersand indicator. If you have int var x5, then nvar gives you the memory address where 5 is stored. You assign that address to the pointer, ptr equals nvar. Now ptr holds the address of var.
Got it. PTR points to var. Now, how do I get the 5 back out using PTR?
You use the dereference operator, which confusingly is also the asterisk in, but used differently. When you put it in front of a pointer variable that holds a valid address, it means go to the address stored in this pointer and get the value there.
So PTR would give me the value 5.
Exactly. In value would PTR would copy the 5 into value. And crucially, you can also write to that location through the pointer, PTR equals 20. This changes the value at the address PTR points to, so the original var would now become 20.
So that's how you simulate call by reference.
Precisely. You don't pass the variable itself, call by value. You pass the variable's address, a pointer, to the function. The function receives the address in a pointer parameter. Inside the function, it uses the dereference operator on that parameter to access and modify the original variable back in the calling code.
Clever. This source example demonstrates this.
Yes, it shows declaring var, getting its address nvar, storing it in PTR, printing var and PTR, showing they're the same value, printing nvar and PTR, showing they hold the same address, usually printed with %, and then changing var via PTR really illustrates the concept.
What about pointer arithmetic? Adding numbers to pointers.
You can do limited pointer arithmetic. You can add or subtract an integer from a pointer, but it's scaled by the size of the data type the pointer points to.
Scaled. How?
If PTR points to an int, and an int is, say, 4 bytes, then PTR plus 1 doesn't give you the address 1 byte later. It gives you the address 4 bytes later, the address of the next integer in memory. PTR plus I gives the address of the ith integer after PTR.
Oh, that's super useful for arrays, since array elements are stored one after another.
Exactly. Array name plus I is equivalent to anerni when working with pointers and arrays. It's fundamental to how C handles arrays efficiently.
Are there pointers to functions too?
Yes, function pointers. These store the memory address where a function's code starts. They allow advanced techniques like passing functions as arguments to other functions, callbacks, creating tables of functions, things like that. Powerful stuff.
What if a pointer isn't pointing anywhere valid? Is there a special value?
Yes, the NLL pointer. NELL, defined in standard headers like edoe.h or aalib.h, is a special value that means this pointer does not point to a valid memory location. It's often just 0 internally. It is absolutely vital to check if a pointer is NOLL before you try to dereference it, PDR.
Dereferencing NALL causes...
Usually, yes, a segmentation fault. It's one of the most common C errors. Always check for NLL if a pointer might not have been successfully assigned a valid address, your example after a failed memory allocation.
Okay, so summing up pointers. They hold addresses, let you indirectly access modified data, enable simulating call by reference, are key to dynamic memory and complex data structures.
And are fundamental to C's power and efficiency. They let you get close to the machine's memory layout.
But they're also the double-edged sword, right, where the danger lies.
Absolutely. Because C gives you this direct memory access, it also gives you the full responsibility for managing it correctly. Misuse pointers, and you get nasty, hard-to-find bugs. Which brings us straight to the challenges of manual memory management.
Right. Memory management in C, often seen as the biggest hurdle. How is memory actually laid out for a running C program?
Understanding the memory map is key. When your program runs, the OS gives it virtual memory, usually split into segments. There's the text segment. This holds your actual compiled machine code instructions, usually read-only.
The program itself.
Yep. Then the data segment holds global variables and static variables that have initial values defined in your code. Uninitialized global statics often go in a related BSS segment, initially zeroed.
Okay. Code and initialized global data. What else?
The two really dynamic areas are the stack and the heap. The stack is for automatic memory management. Local variables, inside functions, function parameters, return addresses, they typically live on the stack.
How does it work?
It's last in, first out, LIFO. When you call a function, its local variables, etc., are pushed onto the stack. When the function returns, they're popped off. This allocation-deallocation is super fast, managed by the compiler OS just by adjusting a stack pointer.
Fast and automatic, but there's a catch.
The stack size is limited, usually quite small, maybe a few megabytes. If you have very deep recursion, many function calls nested, or declare huge local arrays, you can run out of stack space. That's a stack overflow, usually crashes your program.
Ah, the famous stack overflow. Okay, what's the heap?
The heap is the other main memory area used for dynamic memory allocation. This is memory you explicitly request at runtime. Unlike the stack, heap memory is not automatically managed. You allocate it, and it stays allocated until you explicitly free it.
More flexible but manual.
Exactly. You can allocate blocks of any size you need, and they can live longer than the function that created them. But allocation and deallocation on the heap are generally slower than stack operations, and crucially, you must manage it yourself.
So this difference is the core of static versus dynamic allocation.
Precisely. Static automatic allocation happens at compile time or automatically on the stack when entering a scope. Sizes are usually fixed. Dynamic allocation happens at runtime on the heap. Sizes can vary, lifetimes are manually controlled, and that manual control is where the work and the risk lies.
Okay, let's get into those manual heap operations. What are the standard library functions C provides? Found in stdlib.h, right?
Yes, stdlib.h is the place. The main workhorse is malloc. Memory allocation. You tell it how many bytes you need. PR equals malloc, 100.
Okay.
It returns a void, a generic pointer, to the start of that block of memory. You usually cast it to the type you need, like int islet 10 size of
Important points about malloc.
Two huge ones. First, the memory malloc returns is uninitialized. It contains whatever garbage was there before. You need to write your data into it. Second, malloc can fail if there's no memory left. If it fails, it returns NULO. You must always check the return value if IPR NUL. Using an NUL pointer leads to disaster.
Raw, possibly dirty memory must check for NUL. Got it. What about calloc?
Calloc is similar but often used for arrays. It takes two arguments, the number of elements and the size of each element. PR equals calloc. Size of, I'm not going to say difference. The big difference, calloc initializes the allocated memory to all 0 bytes.
Ah, clean memory. That's handy.
Very handy sometimes. But like malloc, it returns void and you must check for NULO.
Okay, what if I need to change the size of memory I already allocated?
That's realloc. You give it a pointer to an existing block from malloc, calloc, or realloc, and the new size you want. New PTR, realloc, old PTR, new size.
How does it work?
It tries to resize the block. It might be able to do it in place, or it might have to allocate a completely new, larger block somewhere else, copy the contents from the old block to the new one, and then free the old block automatically.
So the pointer might change.
Yes. You must always use the pointer returned by realloc, as it might be different from the one you passed in. If realloc fails, it returns NOL, and the original block is left untouched and still needs freeing later. The newly allocated part of a resized block, if it grew, is uninitialized.
Okay, lots of details there. Must check for NOL, pointer might move, new part is dirty.
Right, and realloc has special cases. Realloc NUL size is the same as malloc size. Realloc PTR 0 is the same as free PTR.
And the most critical part, giving memory back when you're done.
Absolutely non-negotiable. You pass it the pointer you got from malloc, calloc, or realloc free PTR. This tells the memory manager that the block is no longer in use and can be reused for future allocations.
What happens if you forget to free?
That's a memory leak, which we'll get to. Important things about free. Passing NALL to free is perfectly safe. It does nothing. But freeing memory that wasn't allocated dynamically or freeing the same block twice, that's undefined behavior. Very bad.
Undefined behavior, the scary C phrase.
Ah.
This manual management leads directly to that minefield of memory errors you mentioned.
Exactly. This is where C programmers earn their stripes or pull their hair out. The power comes with immense responsibility. The sources highlight the classic dangerous errors. First, memory leak.
Forgetting to free.
That's the main cause. You allocate memory with malloc or calloc, use it, but then you either forget the free PTR call or you lose the pointer variable PTR, easy ample, by overwriting it before freeing the memory it pointed to.
So the memory stays allocated but unusable.
Precisely. The program can't access it anymore because it lost the address, but the memory manager still thinks it's in use. Over time, especially in long-running programs, these leaks add up. The program consumes more and more memory, slows down, and can eventually crash the system if it exhausts all available memory.
How do you prevent leaks?
Be meticulous. Ensure every malloc realloc has a corresponding free agreement. Track ownership carefully. Who is responsible for freeing what? Setting pointers to NOL after freeing can sometimes help prevent other errors, but doesn't fix the leak itself. Using tools like Valgrind during development is crucial for detecting leaks.
Okay, leak is lost, but allocated memory. What's a dangling pointer?
A dangling pointer is one that still holds an address, but the memory at that address has already been freed or is otherwise invalid, like pointing to a local variable whose function has returned.
So you call free PTR, but PTR itself still contains the old address.
Exactly. Or you return an local var from a function. The pointer variable exists, but it points to memory that's no longer yours to use. If you then try to dereference this dangling pointer, PTR, to read or write,
Undefined behavior again.
classic undefined behavior, could crash immediately, segmentation fault, could silently corrupt some other data that now occupies that memory location, leading to bizarre bugs later, could even seem to work sometimes, making it nightmarish to debug.
Mitigation.
Best practice. After you free PTR, immediately set PTR equals NUL. That way, if you accidentally try to use it later, dereferencing NUL will likely cause an immediate, obvious crash rather than silent corruption. And never return pointers to local variables.
Yeah, okay. Next up, buffer overflow, the security nightmare.
Indeed. This happens when you write data into a buffer, like a character array used for a string, but right past the end of the allocated space for that buffer.
How does that happen?
Classic cause is using unsafe C library functions like strappy, string copy, or getString from input. They don't check the size of the destination buffer. If the source string or the input is longer than the buffer, they'll just keep overwriting whatever memory happens to be adjacent to the buffer.
And overwriting adjacent memory is bad because
It can corrupt other variables stored nearby. On the stack, it can overwrite crucial things like saved function return addresses. An attacker can craft malicious input that not only overflows the buffer, but also overwrites the return address with the address of malicious code they've injected. When the function tries to return, boom, it jumps to the attacker's code instead.
that's how they take control.
It's a fundamental exploit technique. Consequences range from crashes and incorrect results to severe security vulnerabilities. Mitigation. Never use gets. Use safe, size-aware functions like stringspray, stemtef, which take the buffer size as an argument. Always validate the size of input data before copying it. Use compiler security features and defensive coding.
Really underscores the need for careful coding. What about double free?
Exactly what it sounds like.
Yeah.
Calling free twice on the same memory address, free PTR. This corrupts the internal bookkeeping data structures the heap manager uses.
Why would someone do that?
Usually a logic error. Maybe two different parts of the code think they own the pointer and both try to free it. Or complex error handling paths accidentally free something twice.
Consequence.
Heap corruption. Almost guaranteed to lead to a crash later, often in a completely unrelated malloc or free call, making it hard to trace back. In some complex exploit scenarios, carefully crafted double frees can potentially lead to code execution, similar to overflows, by manipulating the corrupted heap metadata. Mitigation, clear ownership rules, and again, setting pointers to NULL after freeing helps. Free NULL is safe, so a second free PTR after PTRL does nothing.
And finally, the segmentation fault, or seg fault. Feels like the end result of many of these.
Often, yes. A seg fault is the operating system stepping in and terminating your program because it tried to access memory it wasn't allowed to.
Which triggers it?
Common causes include dereferencing an NLL pointer, dereferencing a dangling pointer, accessing freed memory, writing to read-only memory, like the code segment, accessing an array outside its valid bounds, array 10 when the array size is 10, using an uninitialized pointer that contains a garbage address, sometimes Stack Overflow.
The OS just says nope and shuts it down.
Exactly. It protects the rest of the system from a misbehaving program. Mitigation involves all the things we've discussed. Initialize pointers, check for NLL, check array bounds, avoid dangling pointers, manage the stack carefully.
It really is a minefield. The power is immense, but the responsibility is absolute.
It is. And honestly, the difficulty of getting manual memory management right 100% of the time in large, complex C programs was a huge driving force behind the development of languages with automatic memory management.
Like garbage collection in Java or Python.
Exactly. Or compile time safety mechanisms like Rust's ownership and borrowing system. They aim to eliminate these specific classes of memory errors by automating the process or enforcing safety rules at compile time.
So C gives you the raw power and responsibility. Now, besides the core language, you need tools to actually build things. the C standard library.
Yes, the C standard library is crucial. It's not technically part of the C language specification itself, but it's a standard set of header files and functions that every compliant C compiler and environment must provide.
So it comes bundled with the compiler.
Essentially, yes. Its purpose is to provide a standard, portable way to do common, essential tasks: input-output, string manipulation, memory allocation, math, and so on. Using the standard library makes your C code much more likely to work correctly on different systems without changes.
Does its design reflect C's philosophy?
Very much so. It provides relatively low-level efficient building blocks. You won't find massive high-level frameworks like in some other languages. Error handling often involves checking function return values or a global erno variable rather than exceptions. It stays close to the system but provides a portable interface to common OS facilities.
What are the key parts of this library, the essential header files?
The sources list the big ones. Studio.h, standard input-output, is probably used in almost every C program. Functions like print for printing, formatted output to the console, scan for reading formatted input.
And files.
Yes, file operations.
Yep.
Fopen to open a file, fclose to close it, fred and frite for reading-writing binary data, freds and fputs for reading-writing lines of text, essential for file I/O.
Okay, cdo.h for I/O. What else is fundamental?
stdlib.h, standard library utilities. This is where malloc, calloc, realloc, and free live. Also functions for converting strings to numbers, a toy, a tough, generating random numbers, rand, terminating the program exit, and even a standard sorting function, sort, a real grab bag of necessity.
Memory functions are definitely necessities. What about text, strings?
String.h, C strings are just null-terminated character arrays, remember. This header gives you functions to work with them. Strangely safer copy, str-concatenate, str-mp, compare, str-and get length, str-and find substring, and more. Absolutely fundamental for text processing.
Math operations.
Math-h provides common mathematical functions. Squart, square root, pow, power exponent, sin, chorus, tan, trigonometry, logarithms, fabs, float absolute value, ceil, floor, rounding, needed for any numerical work.
Anything for checking character types.
Type. Character classification. Functions like is digit, isalpha, is space, is upper, is lower, let you check if a character is a digit, letter, white space, etc. Very handy for parsing input.
And for debugging.
Assert.h provides the assert macro. You give it a condition that should always be true. Assert pointer.ell. If the condition is false at runtime, assert prints an error message, including the file and line number, and terminates the program. Great for catching logic errors during development.
Like putting sanity checks right in the code.
Exactly. And finally, headers like limits.h and float.h define constants representing the limits of the integer and floating point types on the specific system, like int max, dbl, min. Useful for writing portable code that needs to handle range boundaries correctly.
So the standard library gives you this essential portable toolkit on top of the core language.
Absolutely. Mastering these library functions is just as important as understanding C syntax and pointers for writing effective C programs.
Okay, we've covered C's history, design, syntax, the deep dive into memory management, and its standard tools. And where is C actually used today in 2025? Given all the newer languages, where does it still hold ground?
It holds ground where its core strengths are indispensable. Efficiency, low-level control, portability. The sources paint a clear picture, first and foremost. Operating systems.
Still.
Absolutely. The kernels of Unix, Linux, significant parts of macOS and Windows. Writing an OS kernel demands that direct hardware interaction, fine-grained memory management, and raw speed. C is still the go-to language for this.
The foundation of the system itself.
Exactly, and closely related. Embedded systems and IoT. This is a huge domain for C.
Why C specifically for embedded?
Because these devices, microcontrollers in cars, medical devices, industrial controls, smart home gadgets, are often severely resource constrained. Very little memory, limited processing power. C produces small, efficient code, allows precise hardware control for interacting with sensors and actuators, meets real-time performance needs, and is energy efficient. It's perfect for that environment.
Where every byte and clock cycle matters. Makes sense. Other areas.
Game engines. While high-level scripting is common for game logic, the core engine components, the rendering pipeline, physics simulations like bullet physics, audio processing, often rely heavily on C, or C++, for maximum performance. You need that speed for smooth graphics and complex calculations.
Even the tools that build software.
Yes, compilers, interpreters, assemblers, tools like GCC, the GNU compiler collection, parts of LLVM, the CPython interpreter, many are implemented in C. Building language tools requires efficient text processing, parsing, and often generating low-level code, which C is well suited for.
What about big data infrastructure, databases?
Definitely. Databases and system software. The core storage engines of major databases like MySQL and PostgreSQL have large C code bases. SQLite is written entirely in C. Key-value stores like Redis rely on C's performance for fast data access and efficient memory use, crucial for handling massive amounts of data and high request rates.
Networking, device drivers.
Yep, networking and drivers. The code that lets your OS talk to hardware network cards, graphics cards, USB controllers is typically written in C. Network protocol stacks, like the TCP/IP implementation in the kernel, also use C for efficiency and low-level control needed for packet processing.
And high-end scientific computing.
Scientific and high-performance computing, HPC, large-scale simulations, numerical analysis, core math libraries like BLA, basic linear algebra subprograms, and LPAC, which are foundational for scientific computing and machine learning. These often have highly optimized C implementations to squeeze every last drop of performance out of supercomputers.
It's really striking how C forms the invisible backbone of so much modern technology.
It really does. And the sources point out a common pattern in the modern software stack. C is often used for the performance-critical core, or the low-level plumbing. Then, higher-level languages like Python, Java, Ruby, or JavaScript are used for the application logic, UI, web frameworks parts, where developer productivity and faster iteration might be prioritized.
So C provides the fast engine, and other languages build the car around it.
That's a good analogy. And often, those higher-level languages rely on C libraries under the hood for their own performance. Think of Python's NumPy or SciPy libraries for scientific computing. They provide easy-to-use Python interfaces, but the heavy number crunching is done by highly optimized C or Fortran code underneath.
So C enables the performance of higher-level tools.
In many critical cases, yes. It acts as that foundational layer. This also ties back to C being called the mother of languages.
Because so many languages borrowed from it.
Exactly. C++, C#, Java, JavaScript, PHP, Python, Go, Rust, Swift. Look at their syntax for loops, conditionals, function calls. The C influence is undeniable. Learning C gives you a fundamental understanding of concepts and syntax patterns that reappear across the programming landscape.
Okay, so C is still vital, influential, and foundational. If someone wants to learn it today, why bother? And how should they start? What does its future really look like?
Why learn C today? Well, besides needing it for jobs in those specific domains like embedded or systems programming, learning C gives you a deep understanding of how computers actually work.
Below the abstractions.
Way below. Memory layout, pointers, how software interacts with the OS and hardware. It builds a strong mental model that makes you a better programmer, even if you primarily use other languages. You appreciate why abstractions exist and what trade-offs are involved.
So foundational knowledge, where should someone start learning?
The sources suggest several paths. Classic books are still great. K&R's The C Programming Language, 2nd edition, is the iconic, concise reference, maybe best if you have some programming background already. For a more thorough, modern introduction for beginners, C Programming, a modern approach by K.N. King, is highly recommended.
Other book options?
Sure, Stephen Koshin's books are good. Head for C uses a very visual, engaging style. Modern C focuses on C11, C17 standards. And for digging into the tricky parts, expert C programming is fantastic for experienced folks.
What about online learning?
Tons of options. Online courses on platforms like Coursera, edX often have university-level C courses. Udemy has a huge variety. FreeCodeCamp has excellent free tutorials and projects.
And for quick references or practice?
Websites and interactive tools. Geeks for Geeks Tutorials Point have lots of tutorials and examples. Programmist is good for beginners with an online editor. Learn-c.org offers interactive exercises you do right in the browser. Lots of ways to learn and practice.
So resources are plentiful. Looking ahead, 2025 and beyond, is C's relevance secure?
In its key domains, yes. Its core strengths, efficiency, control, portability, aren't going away for tasks that demand them. The massive amount of existing C code in critical systems needs maintenance and development. Its role as an educational cornerstone keeps introducing it to new developers.
And its place in emerging tech?
Still vital. IoT is growing, and C is dominant there. HPC keeps needing C's speed. Embedded systems in automotive, robotics, manufacturing rely on C's real-time capabilities. It's still the language for building new OS layers or language runtimes. And it's interesting how hardware trends influence C's role. Yes, CPUs are faster, memory is cheaper, which might lessen the need for micro-optimization in some desktop apps. But that same progress enables things like tiny, powerful IoT devices where C's efficiency is paramount, or massive supercomputers where C is needed to harness the power. It remains the essential bridge between software and hardware.
So C adapts its role but remains essential where software meets hardware directly.
That's a great way to put it. It might not be the language you choose for writing a web app, but it's likely running underneath the infrastructure making that web app possible.
Okay, we've covered a lot of ground.
Yeah.
From C's practical origins at Bell Labs, through its standardization, its core syntax, the power and pitfalls of memory management, its standard library, and its enduring relevance in key areas today. It really is a pillar of computing.
It is a language born from utility that shaped decades of programming. Its blend of efficiency, control, and the responsibility it demands is pretty unique.
And understanding it really does feel like understanding something fundamental about how computers work, not just about one language.
That foundational insight is incredibly valuable, I think.
So thinking about that deep dive into manual memory management, all the risks, the dangling pointers, the leaks, alongside the raw power, and comparing it to modern approaches like garbage collection or Rust's compile time checks, it does make you wonder, doesn't it? For the majority of software being built today, does the average programmer truly need or even benefit from C's level of direct, potentially dangerous memory control? Or does the sheer weight of that responsibility, the potential for subtle catastrophic bugs, actually outweigh the performance gains in most cases?
That's a great question. Or, flipping it around, given how much critical infrastructure from the OS on your phone to the libraries powering data science is still built on C under the hood, can you really consider yourself a fully informed, well-rounded software developer in 2025 without having at least some grasp of this foundational language, its principles, and the trade-offs it represents?
Two really interesting questions to leave us with. A perfect place to wrap up this deep dive into the enduring, powerful, and sometimes perilous world of C.